Hi, welcome to your vodcast on box and whisker plotting or graphing. Sometimes this is referred to as box plotting. Now, before I get to that, I wanted to give you a little intro on the reason I'm asking you to do that and actually why we're starting the year with this plotting technique. And it's about probabilistic science. So let me explain that. In your science career so far, you've looked at many areas of science with very specific numbers, with very specific correct values. You know Avogadro's number, right? 6.22 times 10 to the 23rd. You know the speed of light is 2.99 times 10 to the 8 meter per second. You have very precise numbers. But most of science isn't this simple. We don't expect a single number. Rather, we expect a probability represented as a range of numbers in experiments. Let me explain that a little bit with an example. So if I were to do a lab, this is a lab you might do in middle school, right? I give each student 2 thermometers, and one's painted gray and the other's white. And I say, stick it next to the window, and in 5 minutes, see which one's warmed up more, right? And so you might do that, and your results might look like figure 1.4 here. And so we can see that the gray thermometer did have a higher temperature than the white, so you might interpret this as gray thermometers are absorbing more solar energy and thus warming up more, right? And that may be a legitimate interpretation of this data. But of course, you know already that we want replications in science. We don't trust a single experiment to tell us how the world works. So we might collect all the class data and then maybe use the arithmetic mean, right, or average, right? So here again, we have a small difference, but if we're dealing with absolute values, we have a difference, and still it looks like the gray warms up more quickly than the white, and so we might draw conclusions from that. We might draw the conclusion that gray is warming up more quickly than white, right? So how does science or scientists deal with this information? Would they use that same sort of analysis? And the answer really is no. Scientists do use averages to understand the world, but just as importantly, they use spread of data. And so let's take a look at that. Here's how that data might have looked. So each one of these points is a separate student's measurement of their gray thermometer, and here's the white. So you see, here's the distribution of student data. And so you in math class or in science class might have already done linear regression. And so that's one way to look at that scatter of data and compare the amount of scatter, kind of where it's dispersed across our y-axis here, and compare it to this scatter of data and or data. One thing that stands out very quickly, right, is the amount of overlap, right? So if I chose this white bulb here and this gray bulb, you can see this one is much warmer than this one, right? And in fact, if we look at the entire grouping, there's a lot of overlap between all of these individual data points. So of course, if we had run this experiment and gotten these 2 results, we would have the opposite understanding, right? That the white bulb actually warms up more quickly or gets to a hotter temperature. Now, what if we only did 10 replications? It's still possible that we got the top cluster of the white and the bottom cluster of the gray, right? You understand the concept that we did a number of replications and we took the average with the hope that that would get us closer to the truth. But how do we know that we didn't fail to do enough replications? What if we did another 1,000 replications and it turns out that the white and the gray have the same average? So we need a way of understanding how this distribution of results from the white relate to the distribution of results from the gray. Let's look at another representation here. That scatter is much tightly clustered, is much more clustered around our average. And so this is more meaningful, right? We might draw a stronger conclusion that the gray is actually more likely to warm up more quickly than the white. So this is a much more powerful set of data for drawing that conclusion. We may still be able to draw conclusions from this data, but it's weaker. And so as scientists, we might be able to talk about the average, but then we'd have to we'd have to condition our conclusion and talk about this overlap in scatter. What we want to be able to do is compare our two groups. How much overlap is there? Can we determine if our data shows that these two groups are really different? Did we just not sample enough, and thus we're getting essentially the outliers, suggesting that white is warmer than gray or gray is warmer than white, and if we did enough sampling, they would actually be the same? So we're looking for a means of modeling this data so that we can quickly compare our two groups to ascertain not only are they different, but how certain are we that they're different. And this is an important concept, uncertainty in science. All science is truly uncertain to some degree. We accept that in science. It's a hallmark of scientific thinking. But we want to be able to determine how certain we are, in this case, how different gray and white are. And that's where the box and whisker plot comes in handy. Really quickly, I wanted to show you a box plot, and then I'm going to go into how you actually make one and then go deeper into the aspects of the box plot. But here's a box plot comparing bone density for two groups, right? Women and men. So we want to use these two models, or this model of the data, I should say, to compare these two groups. That's the point of using a box plot here. And really quickly, I'll go into more detail, but this is the maximum value for men and this is the minimum value. So between these 2 points are all the values you got on bone density for men. And here we have all the values for women. So we start to get a sense how much overlap, right? If these looked identical, you would say, okay, there's no difference between men and women. But just because there is some difference in how these looks, we want to analyze how much difference so we can actually say, okay, these two groups are actually different. It isn't just that we didn't sample enough. So let me get into that in a little more detail. So here's actually a horizontal box plot with two different data sets plotted, but let's talk about how they actually work. So here's an example. Times it takes for students to walk from the dorm Cookhouse West to Senior Lawn. Let's say I set up shop and counted, and these are various students and times it took them to walk because they didn't catch the shuttle to chew. So I want to know the range or spread, right, the scatter of that walking time. So I also want to have a sense of the median walking time. So the first thing I'm going to do is reorder that data. Okay, so here's how we're going to reorder the data. We're going to take these numbers here, our original set, and we're going to put them in numeric order. Pretty simple. So this 4 here I can cross out because I've moved it here. This 6 I've moved here and crossed that out. This 6 I got from here and crossed that out. And all the way down the line. So all of those I moved here. And if we count them, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. If I had an odd number, and I wanted to find the median, I could just find the center number, and then I'd have, so if I had 15 for instance, I'd have the center number with 7 above and 7 below. That'd be really easy. But since I have an even number, there's no number right in the middle. In fact, it's 9 and 10 are the two middle numbers, right? So to find my median, I would add 9 to 10, divide by 2, and of course I get 9.5. So really my median, oops, there we go, 9.5. Okay, that's my median value. Now, I also want to find the median of the lower set and the median of the upper set. Now, this is much easier because I have, or not much, but a little easier. I've got 1, 2, 3, 4, 5, 6, 7 numbers, 4 all the way through and including 9. So it's an odd number, so I can have 3 above and 3 below my median for this set, which is 7. Right, 3, 4, 6, and 6 is below 7, and then 8, 8, and 9 is above. I can do the same thing for 10 through 22, 1, 2, 3, so this 12 is my median, and then these 3 above. So here I have median for the lower set, median for the whole set, and then median for the upper set. Now, if I wanted to graph those medians, I could use all sorts of graphing techniques, right? You guys are familiar with the line graph, but a line graph shows change over time. Not very useful here. I want to know something about how long it takes the average student to get from Cookhouse West. Bar graphs show categories, right? But I'm not looking at, seniors versus juniors or something like that. Pie chart would be how parts relate to the whole. That doesn't really make sense here. Stem and leaf would be useful, but it doesn't really deal with spreads and medians as well as the box and whisker. The box and whisker is the perfect graph for this. It's what most scientists would use these days for this sort of data. So let me show you how that's done. I'm going to go ahead and draw what is essentially an x-axis. That's about as straight as I can get it with this device. And I'll go ahead and make this 0 down here. And I'll go ahead and make this 25 over here so I can get the whole spread on here. Now I want to plot my median, but before I do, let me see. So this is 0. So if this is 25, then let's say this is 20. And then this is probably about 10, right? And that would make this 5. And this would make this 15. All right. So I'll start with my lowest number 4. So that's probably about here. And then I'll go ahead and plot my median for the lower half, which is 7. So this is 6, 7, probably here. And then my median for the whole value, 9.5, which is roughly here. Then 12, 11, 12, it's roughly here. And then 22, right, which is here. Now, what we're actually going to do is we're going to draw a whisker from our lower value all the way up to our first quartile. Now this value here, this 7, is our first quartile because you'll see we're going to break each part into essentially 25% of the total values. And so we'll draw a line here at our quartile, which is going to be the beginning of our first box. So we already have our whisker here. And we'll go ahead and draw a box all the way over to our median, right, 9.5. There's our first box, and we'll draw our second box all the way up to our next point, right, which was 12, which is our third quartile, first quartile, second quartile, third quartile, and then we'll draw our final whisker. Okay, so now we have from this point to this point represents these numbers. This box represents from here to here, the 9.5, right? This box represents from 9.5 to 12, and then this long whisker represents from 12 to 22, which makes sense because of the spread between 12 and 22. Here's a diagram of a box and whisker graph. So just to show you in a different way, the least value, the lower quartile, the median, the upper quartile, and the greatest value. Okay, but let's get into a little more detail. So let's talk about the interquartile range. The interquartile range is the difference between Q3 and Q1, so the upper quartile and the lower quartile. Let me just show you another image. So this is that interquartile range from here to here. That's what I'm talking about. All right, I want to give you some quick and dirty tips on how to use box plotting to compare two groups. Now, there are various ways of doing this. There's ways of using box plot and mathematically producing a spread. It's called visible spread. But I'm going to have you just use a simplified method for at least our first trimester. So let's take these 3 models of data, so 3 different data sets, obviously, and let's just assume B is our gray thermometers from the beginning of class, or I'm sorry, this lesson, and A is the white thermometers from the beginning of the lesson. So this first box plot, we can see just by looking at the interquartile range. Again, I want you to focus in on the interquartile range. So if you haven't written down what interquartile range is, you better do that right now. here we can see that this interquartile range of B, our gray thermometers, is entirely above the interquartile range of A. So what does that mean? If we think about what these boxes are telling us, this is our lower quartile right here of B, right? So above it is 75% of the data. That means 75% of those gray thermometers were actually warmer than 75% of the A thermometers, right? Because this is the top quartile. That means everything below it is 75% of A's data. So yes, we have some overlap, but that 75% above 75% gives us great certainty. So I would be comfortable with this data set writing down in my report that B is actually greater than A based on this data. And in my discussion, I would note that there is overlap, but statistically speaking, using our box plot as our mode of understanding this data, B is greater than A. Now let's look at these examples. You can see these two examples are a little different. Let's take it piece by piece. Here we have 75% of B's data is not greater than 75% of A. It's greater than 50% of A. So still gives us some certainty that B is greater than A, that gray thermometers warm up more than white thermometers, let's say. So when I write about this in my report, if I were you writing about it, I would write, it is likely that B is greater than A, right? Based on this data, and you'd go into that analysis of the interquartile range and the percent of data above and below to evaluate how likely it is that B is greater than A. Now, let's just compare to this one. Again, we have 75% of B above 50% of A, but you'll notice A has a larger spread. And you might note that, right? Here, A is more tightly clustered, right? This interquartile range is smaller. That means this A group is more consistent for some reason. But still, in comparing B and A, is likely that B is greater than A. Now let's look at the last example here. Here, right, we have 75% of B is not even above 50% of A, right? This interquartile range of B overlaps significantly with the interquartile range of A, right? You guys see that? There's a lot of overlap between these center boxes, the interquartile range. And in fact, the lower quartile is in this box here between the median and the lower quartile of A. So we would not be comfortable saying there's actually a difference between B and A. And of course, you could start by saying, well, look, the maximum of B is above the maximum of A. And if you just look at the median of B is above the median of A. The minimum of B is above the minimum of A. And if you average these numbers, you would find that the B's average is slightly above A's average. But this spread of data is telling us that we can't trust these results to say with certainty that B is bigger than A. Does that make sense? So even if our results are correct for these two groups, we're not certain these two groups are actually different, right? It might have just that we didn't do enough replications. If we did enough replications, it may be that there would be these would look identical. Now, another note on outliers. You still want to show outliers or try to identify outliers in this graphing method. You'll represent them as an asterisk or a circle. Of course, you know that outliers are an extreme value, not typical of the data. These values, we're going to identify outliers as values lying more than 1.5 times the interquartile range away from the nearer quartile. Right, so if it's more than 1.5 times the interquartile range from the nearest quartile, like so Q3 or Q1 here, then you're going to call it an outlier. You still want to represent those so that your reader can understand those data points, but that'll help you manage your data. Here's another depiction of that with a vertical box and whisker graph. Here's some outliers and then all the terms that we've been working with so far. This one has a nice one because it talks about 25% of the data greater than this value, right? So this is 25%, this is 25%, this is 25%, and this is 25%, if I didn't make that clear already. Now, a note of caution. Sometimes you'll see with some whiskers being much shorter than the other whisker, or one side of the box in this case being shorter than the other. That does not mean that fewer values are represented. Remember, it's always 25% of the number of values. But what it means is that those values are grouped more closely together, so they have a smaller spread. And so let's take a look at a couple examples, or an example here. Here you can see the same number of values are between Q3 here and the maximum value as between Q1 and the lowest value. Exact. So if this is 5 values, then this is 5 values. It's just that maybe these have a difference of an absolute value of 1, and the range here is an absolute value of 10, right? So you have a much larger spread. So I hope that makes sense. Now I'm going to put this up, and you can pause it here and take a look at these. These are 1 through 6 steps on how to draft your box and whisker graphs. I put in some good information here that I may not have made clear in my oral description. So take a look at this and make sure you understand it, improve your notes, and you're going to be doing this for your labs.